Hello everyone, my name is Nikunj and I am from MTech IT second year and my roll number is IT 2K2456. My enrollment number is DE2402199. Here we'll be solving assignment 1 of our NAD subject. Assignment 1 includes 7 questions: root finding methods, interpolation, numerical differentiation, numerical quadrature, linear equations, approximations, ODEs. Section 1 of root finding methods. Root finding method, in which first method is bisection method. We'll take assumption fx is on a to b f dot fa dot fb less than 0. Exactly one root exists in between a comma b. Algorithm will take input a b e comma fx. Step 2 will check condition if fa dot fb is greater than 0, then stop no root inside that a comma b. Make assign c is equals to a plus b divides c 2, which is the midpoint. If mod of fc is less than e or b minus a by 2 is less than e, then root is equals to c. We'll stop the algorithm. If f at a dot f at c is less than 0, then we'll assign c to b, or else we'll assign c to a. In step 6, we'll again go to step 3. Time complexity of this algorithm is log 2 b minus a divides e. Space complexity is big of 1. Flowchart of the bisection method is start, then we'll take input abc, abe fx, we'll check condition fa dot fb less than 0, make the midpoint c is equals to a plus b by 2, we'll check the condition mod of fc less than e. We'll check again condition fa dot fc is less than 0. If yes, then b is equals to c. If not, then a is equals to c. Then we'll print our root, which is equals to c, and then stop the algorithm. Second method is regular falsy. Assumptions are this. Algorithm is, we'll take input again, verify fa dot fb less than 0. We'll make c is equals to a minus fa dot b minus a divides fb minus fa. False position formula. If mod of fc is less than e, root is equals to c. Let me tell you guys, this e is equals to 0.0001. If fa dot fc is less than 0, then we'll again make b is equals to c, and else a is equals to c. Then again go to step 3. Time complexity is log of 1 by e. Secant method, these are the assumptions we'll taking. We'll again take input, we'll compute x2 is equals to x1 minus fx1 dot x1 minus x0 divides fx1 minus fx0. If mod of x2 minus x1 is less than e, again 0.0001, the root is x2, we'll stop the algorithm. Or if not, then x0 is equals to x1 and x1 equals to x2, we'll again go to x2 and repeat. We'll again go to step 2 and repeat the same. Time complexity, big O of log 1 by e. Newton's method, these are the assumptions. F dash x should not be equals to 0 near the root. A good initial guess, x not close to root. We have to guess a root close to the root. Input x naught e fx and f dash x. X1 equals to x naught minus fx naught divides f dash x naught. If x1 mod of x1 minus x2 is less than e, then our root is x1. Then we'll stop the algorithm. Step 4, x0 is equals to x1, and we'll go to step 2. Our root is x1. Flowchart of the Newton's method. Start, take input, we'll check by the formula, we'll check the condition, assign x0 is equals to x1, we'll print root x is equals to print is equals to x1, then stop. Error and iteration method. Newton convergence order is 2, secant's convergence order is 1.618, bisections is 1, fixed point iteration. Algorithm is this. Input will take input x0 e and gx, where x is equals to gx, x1 is equals to gx0. If mod of x1 minus x2 is less than e, we'll make root is equals to x1, then stop the algorithm. x0 is will make x0 equals to x1, then again go to step 2 and repeat. Time complexity is log of 1 by e. Question number 2, interpolation method. First is in Lagrange interpolation. These are the assumptions. Xi need not to be equally spaced. We'll take algorithm. We'll take input n plus 1 points and query x. Result will assign result is equals to 0. We'll start loop from 0 to n. Make L is equals to 1. For j is equals to, we'll again start a loop from j is equals to 0 to n, where j is not equals to I, and make L is equals to L into x minus xj divides xi minus xj. Result will is equals to result plus yi into L. Output result as fx. Time complexity is big of n square. This is Hermite input population. We'll take input xi, yi, y dash I for I is equals to 0 to n. Compute li, which is pi of x minus xj divides xi minus xj for j is not equals to a Lagrange's basis. Yeah. Hix is equals to 1 minus 2 multiply x minus I multiply L dash I xi. And we'll get the output hx is interpolated value. Time complexity of this is 0 big of n square. Divide and difference table. These are the assumptions used to build Newton's interpolating polynomial. Set fxi is equals to yi for all I is equals to 0 to n. For k is equals to 1 to n, we'll again interpolate a root I is equals to 0 to n minus k. Then we'll assign values is equals to this like this. Newton's form will be equal to px is equals to fx0 plus fx0 comma x1 x minus x0 and this. The output of the dividend difference table will be px. The time complexity will be n square. And dividend difference table forward and backward. We'll take input f0 to fn, then we'll take height for k. We'll start a loop from k is equals to 1 to n, and again inside that loop we'll start I is equals to 0 to n minus k. We'll take delta k fi is equals to delta k minus 1 f I plus 1 minus delta k minus 1 fi. So we'll subtract f1 minus f0. This will get delta 1f. To subtract delta 1 f1 minus delta f0, we'll get delta square. Newton's interpolation formula. So first is Newton's forward difference algorithm works for equal spacing or equal height. We'll first build the difference table which we recently built. We'll calculate the u which is equal to x minus x0 divided by h. We'll store the result is equals to f0. Term will equals to 1 and k will assign it's 1. We'll start a while loop where k is less than equals to n. Term will become term into u minus k plus 1 divides k. Result will become result plus term delta k f0 and will increase the value of k. Output result. We'll do the same in Newton's backward difference and we'll output the result. Section 3 is numerical differentiation. Differentiation by interpolation. Assumptions are this. Error depends on degree of polynomial and smoothness of f. Algorithm of differentiate Lagrange polynomial. Input n plus 1 point, query point x, order d, first and second derivative. Build a Lagrange basis polynomial. Differentiate L dash ix d by dx of this. F dash x is equals to summation of yi plus L dash I for second derivative. F double dash x is equals to summation of yi dot L double dash ix will give output of the derivative. Time complexity of this algorithm is big of n square. So differentiation by finite differences. We'll take forward differences. Error becomes 0 by h, backward 0h, and central h square. Algorithm for central difference. Input f0 to n, h index I for derivative point. First derivation is df is equals to f I plus 1 minus f I minus 1 divides 2h. In second derivative, fi plus 1 term minus 2 fi term plus 2 fi minus 1 term divides h square. Time complexity is 0 by 1 per point. Question number 4 is numerical quadrature. Newton-Cotes formula. Trapezoidal for n is equals to 1 is this. For Simpsons n is equals to 2. For Simpsons 3 by 8 n is equals to 3 is this. For Riddle or Boole's is equals to n is for Boole's n is equals to 4. This n-point Gauss legendary will take input, will transform x is equals to this Jacobian. This sum is becomes 0, will start a loop, make sum is equals to sum plus weight of I plus fxi, where x is equals to this, will give output as I. Section 5, linear equations. Gauss eliminations. Form augmented matrix for k is equals to 1 to n minus 1. Forward eliminations. Partial pivot. Find max value of aik for I is greater than k. Swap rows. For I is equals to k plus 1 to n. We'll do this, and after back substitution we'll get the value of x. This is a flowchart for it. We'll take input from a matrix, initialize a loop, check forward elimination complete, then we'll start backward substitution. We'll get the x, y, z. The Jacobi iteration method. In this, these are the assumptions. Initial guess x0 given often 0 vector. We'll take input as A n cross n matrix B n. Repeat for I is equals to 1 to n. We'll do this for this loop until maximum value of xi minus xik is less than e. Will give output x comma k plus 1 term. Jacobi-Seidel method. Same as Jacobi, diagonal dominance ensures convergence. Converges faster than Jacobi in most of the cases. Uses updated values immediately in the same iteration, not parallelizable sequential updates. Step 1 will take inputs A n cross n matrix, B n matrix. Repeat. We'll start a loop 1 to n, then perform and assign this value to x. Step 5 until we get the maximum value of xi new minus xi old is less than e. We'll iterate it. Time complexity is n square into iterations. Section 6, approximations. So least square approximation, which this is question 6 of the question. M data points xi, yi are given with m greater than n plus 1. Algorithm. Step 1, input m points, build normal equations A transpose A dot C A transpose Y, solve n plus 1 into n plus 1 system for coefficients C, compute residual. Question number 6.2, polynomial approximation via orthogonal polynomial. Its algorithm is choose family legendary and degree n, generate psi 0, psi 1, psi n for using 3-term recurrence, compute coefficients, approximate px is equals to summation of ck psi k for k is equals to 0 to n. Output px and error estimate. Question number 7, ordinary differential equation. Euler's method, assumptions and algorithms. Algorithm will take input, will assign x and y, while the condition is x less than x e and d. Will do Euler's method, y is equal to y plus h, x is equal to x plus h, print x and y, stop. Time complexity of this algorithm is 0, big of n. Flowchart is, we'll start the flowchart, start the program, take input, assign x and y, checks condition of x, if no, stops, if yes, y becomes this and x becomes this, we'll print x and y and then stop again. Runge-Kutta method. fxy is sufficiently smooth, fifth derivative exists. Step size h chosen for stability. H must not be too large. Fourth stage RK4 is standard fourth order arithmetic function evolution. Step 1, input fxy x0 y0 h while x is less than xn, k1 is equals to h multiplied by fxy, k2 is this, k3, k4, and after calculating all 4 k's, we'll calculate y is equals to yi plus k1 plus 2k2 plus 2k3 plus k4 dividing 6. We'll assign x is equals to x plus h, then we'll get our values x and y, and then we'll print the x and y and stop the algorithm. Time complexity is big of n, it has 4 evolution steps. Flowchart of the Runge method is this: start, take input, check condition, calculate k1, k2, k3, k4, calculate y, and then stop after getting x and y. So summary complexity of all the method. These are the methods we have used in this video, and this is the time complexity and this is complexity and the order of conversions. So thank you. I hope you have understood the assignment 1.